Hello, thanks for joining me for this talk. We'll be looking at the nonlinear Brascamp-Lieb inequality. If you don't know what a Brascamp-Lieb inequality is, much less a nonlinear one, don't worry, I'll tell you all about it. So I'm Taryn Flock. I'm at Macalester College in St. Paul, Minnesota. And this talk, as you know, is part of the Fourier Restriction Online Workshop 2021. So in this talk, I'll start by introducing sharp inequalities, which have been the focus of a lot of my research and will be an important tool in our proof of this nonlinear Brascamp-Lieb inequality. But more importantly, I will tell you what on earth is a Brascamp-Lieb inequality. And then we'll take a look at the statement of the nonlinear Brascamp-Lieb inequality, as well as just sort of a moral perspective on the fact that understanding the constant in the inequality allows us to prove stronger versions. I'll say just a few words about the proof, and I'll say even probably a few less words about a connection to computational complexity. The classical example of a sharp inequality comes to us from Carthage, where Queen Dido was told that she could have as much land as she could enclose with the hide of a cow. And she cut this cowhide into a ribbon and was then had the problem of, given this fixed length of, we'll think of it as fence, how can we enclose the most area? How can I have the largest city possible? Symmetry suggests the circle is your best bet, or if you're dealing with a coastline, perhaps you want a semicircle. And this is, in fact, the case. So the isoparametric inequality tells me that for any shape in the plane, the area of this shape is at most 1 over 4 pi times the perimeter of the shape squared, with equality if and only if we're looking at a circle. So as we remember, the area of a circle is pi r squared, whereas the perimeter is 2 pi r. So squared and divided by 4 pi, we have exactly equality. When I call this a sharp inequality, this is firstly because we have the best possible constant. We have 1 over 4 pi. It's certainly true to say that the area of the shape is smaller than the perimeter squared, but we're off by a factor of about 12. The area is like 12 times smaller than the perimeter squared, and it's interesting to know that. And moreover, we know when we have equality. The sharp inequality contains the geometric information that the optimal value is the circle. It's worth noting that the case of equality may not always exist. If I limit my shapes to polygons, well then I can get closer and closer to this pi r squared circle story by taking more and more and more and more sides on my polygon, but I'll never actually achieve equality. My polygon is becoming more and more like a circle, but never gets there. In our functional examples, the analog of this will be functions that sort of condense into Dirac masses at a point. So it may be that we leave the space of functions as we approach the optimal configuration. This is the very general question that I like to consider in my research. Given some inequality, like area of a shape is smaller than perimeter squared, what is the best possible constant? Is it actually that area can be 12 times bigger than the perimeter squared, or is it 12 times smaller? Moreover, are there inputs that actually yield equality? We'll refer to these as extremisers. What properties do they have? Are they symmetric, like circles, for example? Or in terms of functions, are they differentiable? Are they, what sort of asymptotic decay do they have? Can I, if I'm very lucky, write down a formula? What's the properties here? And more generally, what can I say about inputs that nearly achieve equality, about sequences that are getting closer and closer and closer to this equality case, but don't necessarily, do they converge? Is there compactness? If I look at my inequality, right, the optimal constant will always be this solution to left-hand side over right-hand side is less than or equal to constant. So this constant is some maximum or supremum. If there isn't an extremizer, it's just a supremum, not a maximum. And we can ask about these sequences that must exist. Do they converge? Is there some compactness? And once I've answered these questions, can I use this information to strengthen the inequality? If I'm not in the equality case, can I use some sort of quantitative measurement of my distance from equality to make quantitative improvement in the inequality? Is one direction that this is taken. Here in this talk, we're going to look at a different version where we use the understanding of the optimal cases for a linear inequality to prove a nonlinear variation on that inequality. So what is a Brascamp-Lieb inequality? Well, it's a generalization of sort of our familiar inequalities that tell us about when the size of a product is bounded by the product of the sizes. Note, I'm assuming that my functions are non-negative, and this assumption is harmless because the absolute value of the integral is less than the integral of the absolute value. So our first example is Hölder's inequality, where I look at the product of two functions and observe that the size of the product is bounded by the product of the sizes exactly when my LP spaces match up in an appropriate way. If I have L2 and L2, I have Cauchy-Schwarz's inequality. If I have L1, L infinity, I have what I tell my calculus students is the area estimate. So this is our first example of a Brascamp-Lieb inequality. Our next example is Young's inequality. This is a sort of dual form, right? We've added this H, dual form of Young's convolution inequality. We have the product of these three functions with something a little bit more complicated going on is bounded by the product of their sizes, as long as the sizes are chosen to be compatible. Our next example is the Loomis-Whitney inequality, where I consider a product of three functions, and I'm integrating over the space R3, but what I'm really doing is taking a projection into all but the first coordinate and evaluating f1 there, then taking the projection into all but the second coordinate, evaluating f on those two variables, and then taking the projection into all but the third coordinate and feeding that information into f. And in that case, the product of these three functions is bounded by their product of the sizes, if and only if the sizes are compatible, and here the only possible option is that we choose L2 in all directions. This inequality has some beautiful geometry behind it and actually relates back, sort of obliquely, to the isoparametric inequality that we started with. But I don't have time to tell that story in this talk. So what is the structure that unifies these three inequalities? What are we generalizing when we talk about a Brascamp-Lieb inequality? Well, I have the size of the product bounded by the product of the sizes, but there's something more complicated happening here with the domain on which I'm evaluating f. Right? I'm taking the domain of integration and projecting it into a lower dimensional space for my functions to be evaluated on. So I can think of this as the integral of a product of functions composed with a family of linear maps. And it's this structure that will define a Brascamp-Lieb inequality. Here's our statement of the Brascamp-Lieb inequality. More than a single inequality, it's really a very general family of inequalities. Perhaps their defining feature is that they are multilinear. So to set these up, we're going to take m and n to be positive integers. N is the dimension of the space I'm integrating over. M is the number of functions in my product. And for each function, I'm going to have a linear map that I compose the function with. This linear map needs to be surjective. If it's not, the story sort of falls apart and isn't interesting. And so given a family of linear maps and a family of powers, our understanding of the size of the functions, we have a Brascamp-Lieb inequality, which says that the product of the functions is bounded by a constant times the product of the sizes. Now, of course, this constant may well be infinite unless I place some restrictions on the family of powers P and the family of linear maps L. As we saw on the last slide, P can't just be anything given a family of linear maps. Brascamp and Lieb introduced these inequalities in the 70s in the case where the target dimension of these linear maps is all 1. As a generalization of Young's convolution inequality, at the time they were investigating best constants for Young's convolution inequality, but prove the result for these more general form of multilinear inequality. What do they prove? They prove that to find the best constant, it's enough to consider Gaussians. Or, from a slightly different perspective, if you want to understand is the best constant finite, it's enough to consider Gaussians. To understand optimal configurations, Gaussians really do tell the full story. In 1990, Lieb generalized this result to the full family of Brascamp-Lieb inequalities. So to understand, is the Brascamp-Lieb inequality finite? What is the best constant? Well, it's enough to consider functions of the form e to the matrix paired with x. So all we need to do is check all of the possible Gaussians ever, and if the Brascamp-Lieb inequality is finite, then it's finite. So that's it, we're done. We know all we need to do Gaussians. That'll explain everything, right? We're done. So it turns out checking on Gaussians doesn't quite tell me the whole story because the computation is a bit of a mess. I do get a formula for the best constant in my Brascamp-Lieb inequality as a function of the linear maps and the choice of powers p. But this is a supremum over all positive definite matrices of a product divided by a product of determinants divided by a determinant of a sum. And this isn't all that simple to determine even, is it a finite number, yes or no? So there were several partial results leading up to a breakthrough in 2008. In 2008, Bennett, Christ, Carberry, and Tao gave a characterization of which families of linear maps and powers p give rise to a finite Brascamp-Lieb constant. We're required to have an appropriate scaling condition. Think the 1 over p plus 1 over q is equal to 1 in Hölder's inequality. And we're also required to have a dimension condition that is morally telling me that the kernels of these linear maps line up in an appropriate way dependent on my p's. Think the fact that Loomis-Whitney, where my kernels are each of these coordinate axes, only works when all three functions are measured in L2. So now let me tell you a bit about my own work on Brascamp-Lieb inequalities. So the first result that I was able to prove with my collaborators is that the Brascamp-Lieb inequality is a locally bounded function of the linear maps. Morally, the geometries that give me finiteness, this alignment of the kernels story, is actually stable under perturbation. This is not clear from that supremum over positive definite matrices formulas that you look at from Lieb's theorem. So this is already enough for many applications, including Bourgain, Demeter, and Guth's proof of the Vinogradov mean value theorem. But over the years, we've proved more. Specifically, the Brascamp-Lieb constant is actually a continuous function of L, and moreover, well, not listed on this slide, the same paper that contains the nonlinear Brascamp-Lieb theorem shows that the Brascamp-Lieb constant is actually Hölder continuous, though the degree of Hölder continuity depends on the family of powers p. This brings us to the central result of this talk, a nonlinear Brascamp-Lieb inequality. So we've generalized the Brascamp-Lieb inequality by replacing our linear maps with a family of nonlinear maps, as the name suggests. What do we require about these nonlinear maps? Well, we require that they are differentiable and a little bit better than differentiable. We require that the derivatives of these nonlinear maps are always surjective, and that the family of linear maps that are the derivatives at some point, up to translation, we can consider it to be 0, give rise to a valid Brascamp-Lieb inequality. So I have these family of nonlinear maps. Near some point 0, their derivatives give me a true Brascamp-Lieb inequality. In that scenario, then, a nonlinear Brascamp-Lieb inequality holds on a small neighborhood of the point. So we've changed the Brascamp-Lieb inequality in two ways. First, we've composed with these nonlinear maps, but secondly, we've restricted our attention here to a local neighborhood. Where the linear Brascamp-Lieb inequality was global, this inequality is only giving us something local. Though in a compact setting, you might hope to piece, you can piece these local versions together to get a inequality on the compact region. One application of such a nonlinear inequality is to consider the case where these nonlinear maps incorporate the atlas maps of moving from some manifold into Rn. And what the nonlinear Brascamp-Lieb inequality tells me is that for your favorite linear Brascamp-Lieb inequality on Rn, there is a version on the manifold, at least locally. This very general result follows on the path of many prior results, giving nonlinear Brascamp-Lieb inequalities in special cases. Bennett, Carberry, and Wright proved a nonlinear Loomis-Whitney inequality. Bennett and Bez proved a nonlinear Brascamp-Lieb inequality under the condition, very similar to Loomis-Whitney, that the kernels of these linear maps, their direct sum is all, they span Rn, is Rn. Zhang in 17 gave a nonlinear version when these nonlinear maps are in fact polynomial. One might hope for this polynomial version to generalize to tell the full story, but the proof uses polynomial partitioning, and because of that gives bounds that depend strongly on the degree of polynomial. I like understanding sharp constants, and this inequality actually even tells me a little bit more about the constant in my nonlinear inequality. So we find that the best constant in the nonlinear inequality is, for an appropriately small neighborhood, 1 plus epsilon times the best constant in the linear inequality. What's interesting, one thing that's interesting, is that our proof gives this result for the sharp constant, and I don't know of a simplification of the proof that would give the nonlinear inequality without this control on the constant. As I've said, sharp constants, extremizers, and extremizing sequences are a tool that I hope to use to strengthen and understand inequalities. So how do extremizers contribute to our understanding of nonlinear Brascamp-Lieb? Well, the key lemma that we prove along our way to showing this fully general nonlinear Brascamp-Lieb inequality is some quantitative control on functions and tuples of functions that nearly achieve equality. And what that is a quantitative version of Lieb's theorem. Lieb's theorem told me that I could understand the best constant in the Brascamp-Lieb inequality by understanding this supremum over all positive definite matrices. And what we find is that we relax our control on the constant a little and want to get within a factor of 1 minus delta of this best constant. Well, we can do that using positive definite matrices that satisfy some quantitative control on their eccentricities. So the concern with extremizing sequences is that they might not converge to Gaussians. We know this is a sequence of Gaussians, but it's possible that these Gaussians, and this does in fact happen, that these Gaussians sort of have some fundamental domain where most of the mass, right? What am I drawing here? I'm drawing this like fundamental region where most of the mass of the Gaussian lives. And there are examples where, as we approach the extremal configuration, these Gaussians spread out their mass to become essentially a Dirac mass on a lower dimensional vector space. And what we find is that even though this is happening, we can get close to the best constant without using Gaussians that are too eccentric. We have quantitative control on the level of eccentricity. So how does the proof go? The fundamental idea of the proof is induction on scales. If I assume that my function is approximately constant at some small scale, then the function won't see the nonlinearity. And so I can have an estimate on that small neighborhood just from the linear estimate. And our goal is to understand a whole neighborhood by dividing into smaller scale pieces without losing too much. And the key here is using these Gaussian near extremizers with controlled eccentricity to do our division of space. It's precisely the ability to use these Gaussians to localize that gives us the control to not lose too much in our induction on scales argument. There are, of course, several more technical details to make this go through. Gaussians don't actually play very nicely with this assumption that the function is constant at some given scale. And so we have to sort of truncate our Gaussians and allow the exact degree of constantness to vary by scale, which is an added layer of complexity from a standard induction on scales argument. The last thing I want to mention is a surprise appearance of the Brascamp-Lieb constant in computer science. You may have heard of the matrix scaling algorithm. This is a classical tool for improving the computational fitness of a matrix. It proceeds by successively improving the matrix until a predetermined fitness condition is reached, and this fitness is measured using the determinant. In the 2000s, this algorithm was generalized to the setting of operators, or here you can also think of symbolic matrices. So these are matrices that are defined in terms of a family of linear maps, just like our Brascamp-Lieb inequalities. This operator scaling algorithm again proceeds by making successive improvements until a appropriate fitness condition is reached, and this quantity is measured in terms of quantum capacitance. So this is a number sort of like a determinant related to a family of linear maps. And the surprising fact is that this quantum capacitance is the reciprocal of the Brascamp-Lieb constant, the best constant appearing in our multilinear inequality. Thank you so much for your attention and coming to listen to this video presentation. I look forward to chatting more during the discussion sessions.